This is the last method of integration that we'll cover before Exam 1, and it's called the method of partial fractions. We use it for integrating rational functions, and in particular proper rational functions. So let's define what these are. A rational function is a function that is a quotient of two polynomials. Now, if you don't know exactly what a polynomial is, I suggest that you Google it and find out. The rational function has a numerator and a denominator, each of which are polynomials. A proper rational function is one where the degree of the numerator is less than the degree of the denominator. So let's say we have a function f of x, a rational function, that is, I'll call it n of x over d of x, where n and d are polynomial functions. F is proper if the degree of the numerator function is less than the degree of the denominator function. And if it is not proper, we can use long division to write it as a sum of some other polynomial plus a proper rational function. Let's look at some examples of rational functions that are not proper. Here we see the degree of the top and the degree of the bottom is both 2. So we must use long division to rewrite the integrand. So I take x squared plus 1 and divide it into x squared. And you're always just looking really at this first term here in the divisor. X squared goes into x squared once, and multiply by 1, we get x squared plus 1. Now you subtract. Now you can just, if you want, you can just change the sign and add. So if you wanted to, I think of it as just subtracting, but you could change the sign to minus and change the plus to a minus, and then adding, you have 0x squared minus 1. So as soon as the degree of this remainder is less than the degree of the divisor, we can't divide any longer, and we write this as the integral of 1 minus the remainder 1 over x squared plus 1 dx. Now we've done this in class before, so you can I hope you remember. It's really no different than writing 7 halves. Dividing 2 into 7, we would get 3 plus a remainder of 1 over 2. Dividing 2 into 7, dividing denominator into numerator, we would get 3 with a remainder of 1. Here, dividing numerator by denominator, we get 1 with a remainder of minus 1. We write it the same way. Oh, well, we can integrate this, so there's no special technique of integration that we need at all here. This rational function is one we know the antiderivative for. So integrating 1 dx, we get x, and then we have minus the arctangent of x plus a constant. So in this example, there was no special technique. We just made the rational function proper, and we knew how to integrate each part. So we'll look at 2 more examples of where we need to first make our rational functions that we need to integrate proper. So we see the degree of the numerator in this first example is 3. The degree of the denominator is 2, so it is not proper. So I take the denominator, x squared plus 1, and I'm going to divide it into the numerator, x cubed. Just looking again at the first term, or the highest degree term. So x squared goes into x cubed x, and multiplying x times x squared plus 1, I have x cubed plus x. Now I'm going to subtract. So x cubed minus x cubed is 0, and I just have minus x. Now, the degree of this remainder is less than 2, the degree of the divisor, so we're done. And I can write this integral as the integral of the quotient x plus, well, it'll be minus because it's minus x over x squared plus 1 dx. Again, in this example, we don't need to have any special way of integrating because we know how. The integral of x dx is 1/2 x squared, and then we have minus the integral of 1 over x squared plus 1, and we have an x dx. This is a simple substitution. If u was equal to x squared plus 1, then du is 2x dx, and I need to adjust with 1/2. So we have there the integral of 1/2 the integral of 1 over u du. So our solution would be, or our integral, indefinite integral, 1/2 x squared minus 1/2 the natural log of x squared plus 1. I'm not using absolute value because the argument of the natural log is always positive in this case. So there's our antiderivative. We did not use any special technique. All we did was make the rational function proper, and in both of our last examples we saw immediately how to integrate by either using arctangent or simple power rule or a simple substitution. Our next example is another one that is not proper. I'm doing 3 of these because I know that in the past students need practice in dividing these polynomials. It's not something you probably have done in a long time. So we have to divide. The degree of the denominator is 1. The degree of the numerator is 3. So we have to divide x cubed minus 2x plus 1 by x plus 2. Again, just looking at the highest degree term. X goes into x cubed, x squared times x squared is x cubed plus 2x squared. So now if you wish, you could change the sign. We're going to subtract. So change the sign and add if you like that. So we have these always will go away, the first term here. And we have minus 2x squared minus 2x plus 1. Adding these two polynomials together, just add them together if you change the sign. Okay, so the degree is still 2, so I have to divide again by x. X goes into minus 2x squared minus 2x times. Multiplying, I get minus 2x squared. And then I have minus 2x times 2 is minus 4x. So again, I'm going to change the sign and add. So this becomes plus and this minus becomes plus. And now I add them, these two polynomials, and I'll get 0. Here I have minus 2x plus 4x, or 2x plus 1. I'm still not done. X goes into 2x plus 2 times, and multiplying I get 2x plus 4. Changing the sign, minus plus 4 changes to minus 4. Adding them together, I get negative 3. So now we're done, and this problem becomes the integral of, well, the quotient is x squared minus 2x plus 2 minus 3 over x plus 2. Well, again, we're not going to need any special technique of integration. Once we make this proper, often we see right then how to do it. We just use the power rule on x squared minus 2x plus 2, and here we can see we have a natural log. So we have 1/3 x cubed minus x squared plus 2x minus 3. Now, I do want to double check. If u was x plus 2, then du is dx. So yes, this is the natural log of the absolute value of x plus 2 plus a constant. All right, so that should bring back to your memory how to divide one polynomial by another, and stress the fact that we do want to make any rational functions proper, and often when we do, we'll just be able to integrate right then. But our next examples will use the method of partial fractions to integrate proper rational functions. Now, this is a rational function. It has a degree 1 on the top polynomial and on the bottom a polynomial of degree 2, so it is proper. Now, granted, you could split this using the numerator and write x over 1 minus x squared plus 3 over 1 minus x squared. But you wouldn't know how to integrate the 3 over 1 minus x squared. So I'm just going to leave it together and show you a different method of doing this. Excuse me, everybody, I opened up the wrong example. That will do in another couple examples. So let's forget that last one right now. Any rational function, p of x over q of x, can be written as a sum of partial fractions. That is, other rational functions whose denominators are either irreducible factors of q of x or powers of those factors. If p of x over q of x is proper, the partial fractions will be ones that we know how to integrate. Now, I just want to show you an example. That's a lot of words there. Here's an example of a p of x over q of x. P of x has degree 3, and q of x, if you look carefully there, has degree 4, so it is proper. And the denominator polynomial is factored. And what it said above is that a rational function can be written as a sum of partial fractions. So here you have this fraction, smaller, they're rational functions, a sum of rational functions, where the denominators are factors of the denominator here. Notice we have one partial fraction with denominator x, another one with denominator 1 plus x squared, and another one with the linear factor x plus 2. Now, I'm not showing you how we get these partial fractions, but this is a true statement, and you see that if you factor the denominator, you at least know what the denominators of your partial fractions will be. The part that we have to learn is how do you find out what the numerators are. So I'll show you how to do that using this example. We take our integrand, which is a proper rational function. Make sure it's proper before you start this process. It is proper. I would not know how to integrate that. If it were 1 plus x squared, we'd have an arctangent, but I don't have an x. If I let u be 1 minus x squared, I don't have enough to make my du, and so I'm going to use the method of partial fractions. I take my denominator and factor it. So I have 2 over, and this is easy to factor, 1 minus x times 1 plus x. So we have this denominator factoring into the product of two linear polynomials. Now here's how it'll set up. 2 over 1 minus x times 1 plus x will be equal to a over 1 minus x plus b over 1 plus x. It will split into the sum of two partial fractions, each with a denominator which is a factor of 1 minus x squared. Now, any time that you have a linear denominator, then the numerator is just going to be a polynomial of 1 degree less. Well, we have linear, so the numerator here will just be a constant. Anytime you have a linear factor in your partial fractions, a linear denominator in a partial fraction, your numerator is just a constant. So we have to solve for a and b. And here's what you do. Multiply both sides by the denominator, 1 minus x times 1 plus x. Now, normally you're not going to have to write this out all the time. It's easy. But first time, let's do it. We're going to multiply both sides by 1 minus x times 1 plus x, and we see that our denominator will cancel completely here, and we get 2 is equal to, here the 1 minus x's cancel. I have a times the quantity 1 plus x plus b, and here the 1 plus x's cancel, and I have times the quantity 1 minus x. Now we're saying that this is true for all x. So I want to solve for a and b, and the easiest way to do it, since it's true for all x, let's pick a couple easy values of x to plug in. In other words, if x is equal to 1, I'm choosing it looking right here, if x is equal to 1, then b times 1 minus x will be b times 0, and it just drops out. So if x is equal to 1, then this says that 2 is equal to a times 1 plus 1 is 2 plus 0. Well, I won't bother to write that. This tells me that a is equal to 1, so I solve for a. Now there's another really easy value of x that we could plug in. If x is equal to minus 1, it's going to make this factor equal to 0, and that will give us the equation 2 equals 0 plus b times 1 minus a negative 1 times 2. So b is also equal to 1 here. Well, once we've solved for a and b, then I can rewrite this integral. I can say that the integral we started with now is the integral of a 1 over 1 minus x plus b 1 over 1 plus x dx. Now with the u substitute, I think I'm going to split these, because the reason I'm going to split it into two integrals is because I would have a u substitution here that I need to use that would not be suitable for this one. So I'm going to write the integral of 1 over 1 minus x dx plus the integral of 1 over 1 plus x dx. Well, in the first one here, if u were 1 minus x, then du would be minus dx. So I'm going to make that minus dx and adjust here with a minus. On this one, if u were 1 plus x, then du is dx. No adjustment necessary. So let's now just integrate. In each case, we have an example of 1 over u du. So we get as our integral, this is equal to minus the natural log of u, which was 1 minus x, an absolute value, plus the natural log of the quantity 1 plus x, an absolute value, plus a constant. So this was your first example of where we used partial fractions. You factor the denominator and then set up the partial fractions and solve for the numerator. Here's the other example that I tried to start a little too early. Notice it has the same denominator, 1 minus x squared, but it's still proper. The last one we did was just 2 over 1 minus x squared. Here we have x plus 3 over 1 minus x squared. So we just do exactly the same thing. We take x plus 3 over, well, it's 1 minus x times 1 plus x. You factor the denominator. These are both linear denominators. We're going to have a denominator of 1 minus x. We're going to have a denominator of 1 plus x. Each of these factors gives rise to a denominator that is linear. Therefore, we will have a and b as our numerators, just constants. Okay, so let's solve for these. We're going to do exactly the same thing. I'm going to multiply both sides by this denominator. Multiply both sides by the denominator, 1 minus x times 1 plus x. Really, you don't need to write it down. 1 minus x times 1 plus x. You know everything cancels here, and we get x plus 3 is equal to, the 1 minus x goes, and we have a times 1 plus x plus b times the quantity 1 minus x. Now again, we want to let x be little values that will allow us to solve for a and b easily. Well, if x is equal to minus 1, then a will disappear because we'll have 0a. So if x is equal to minus 1, this tells us that minus 1 plus 3, 2, is equal to 0 plus b times 1 minus negative 1, or 2. And again, we have b is equal to 1. Well, let's try x equals plus 1. Back up here, plugging in values of x. We get 1 plus 3 is 4, is equal to 2a plus 0. So in this case, a is equal to 2. And we have then this integral, this here that we started with, is equal to the integral of a 2 over 1 minus x dx. I'm going to split them right away, and plus the integral of 1 over 1 plus x dx. b was equal to 1, a equals 2, yes. Okay, so now we need to integrate both of those, which is actually quite easy. Again, they're both just natural logs. And let's see, for the first one, if u is equal to 1 minus x, du is minus dx, and I need to adjust on the left with a minus. So I have minus 2 over u du minus the natural log of 1 minus x in absolute value. And here, if u is 1 plus x, du is dx, so no adjustment needed. The natural log of the absolute value of 1 plus x plus a constant. So this turns out to look much the same, but again, we did it exactly the same way as we did the previous example. In this example, it's certainly proper. The bottom is degree 3, the numerator is degree 0. It's constant. And it's all factored for us, and we cannot factor any further. This polynomial here, this quadratic, degree 2, is called irreducible. An irreducible quadratic. I cannot factor it any further. And an irreducible quadratic, the way you can always tell that it cannot be factored, if you have ax squared plus bx plus c, if it's irreducible, that means it has no real roots. It doesn't cross the x-axis, so the discriminant b squared minus 4ac has to be negative. The discriminant, the part that's under the square root in the quadratic formula. If there are no real solutions, then that has to be a negative number, leaving our solutions to be complex. And we cannot we cannot further factor that. So in this case, we have a linear and an irreducible quadratic factor. And this is how you break this one up. 18 over x plus 3, a linear, and x squared plus 9, irreducible quadratic, is going to be, well, it's going to give us a fraction with denominator x plus 3, and it's going to give us a partial fraction with denominator x squared plus 9. The numerator, if the denominator is linear, the numerator is just a constant. If the denominator is a degree 2, an irreducible quadratic, then the denominator is linear. So we've used a, so I'll say bx plus c. An irreducible quadratic denominator gives us a linear numerator, and a linear denominator will give us a constant numerator. So we're going to again multiply by the denominator on both sides and clear the fractions and solve for a, b, and c by using convenient values of x. Okay, so let's clear the denominator, and I'm not going to write all of this out. I'm just going to multiply both sides by that product. It'll all cancel on the left, and I'll simply get 18 is equal to. Now I'm multiplying each of these terms by this product that is the denominator on the left-hand side. So when I multiply it to the first term, the x plus 3's cancel, and I have a times x squared plus 9, the quantity. Plus, now when I multiply that denominator to the second term, then the x squareds plus 9 cancels, and I have the quantity bx plus c times the quantity x plus 3. Now I need to solve for a, b, and c. Well, a convenient value, well, x equals minus 3 would be a good one. So let's let x be minus 3 first, and then I know that this will become 0, which will wipe out my entire second term in the sum there. So if x is minus 3, I get 18 is equal to a times, okay, minus 3 squared, that's 9 plus 9 is 18. And this will all be 0, plus 0. So that tells me, oh, that's nice, a is equal to 1. So I have solved for a. So I'm going to, rather than rewrite everything, I'm just going to put a 1 here for now. Well, we have this. This is going to be 1 up here. A will be 1. We solve for that. Now the next convenient value for x will have to be x equals 0, because at least it'll wipe out the b, and we already know a, so we'll be able to solve for c. Okay, so if x is equal to 0, we get, let's use 1 for our a. So we have 18 is equal to x is equal to 0, so 1 times 9 is what we have there. A times 0 squared plus 9, plus, well, bx, that's 0, so I just have c times 0 plus 3. So this tells me that my 3c is equal to, subtracting 9 from both sides, gives me another nice value, c equals 3. So we have solved for c. c is equal to 3, and I think I will put 3 here, and I'll go up here and put 3 just to keep track of what we're doing. And now we still have to solve for b. And really, we might all choose a different convenient value for b. I think I will choose, well, I don't know, maybe b equals 1. You could choose anything but b equals 0, because we want, x equals 1. You don't want to choose x equals 0. We've already done that. Let's just choose x equals 1. That's easy to plug in. So you see on the left we just have a constant. No value of x is going to change the left-hand side. So 18 is equal to x squared. 1 squared plus 9 is 10 times 1, 10, plus b times 1 is b plus 3, the quantity, times 1 plus 3 is 4. So we can solve for b. 18 is equal to 10 plus 4b plus 12. So that's 22. Subtracting 22 from both sides, I get negative 4 is equal to 4b. So we have then b is equal to negative 1. So we have our three coefficients, and let me go back up to the integral. Let's see, what was b? We have a is 1, c is 3, and b is negative 1. So if we go back up to here, we see b is negative 1. So it just becomes minus x. So our integral then is, our integral was the integral of 18 over x plus 3 times x squared plus 9. And we have now solved for the partial fractions, and I'm going to split it up into two. 1 over x plus 3 dx, and we have plus the integral of minus x plus 3 over x squared plus 9. Alright, well the first one, that's easy. That's a natural log. Ux plus is x plus 3, du is dx, so we have immediately the natural log of x plus 3. But now this one, well, it's a little more complicated. Now, this is irreducible, so we're not going to use partial fractions. You can't factor it anymore. So I'm going to split. So I'm going to split using the numerator always. I'm going to write this as the integral of minus x over x squared plus 9 dx plus the integral of 3 over x squared plus 9 dx. Now this is a complicated problem. It's going to take us a while to solve it. We have to integrate, well, the second one, can you see that's going to be a natural log? Let's just make our little adjustment. If u is x squared plus 9, du is 2x dx. So I need, my x is here. I'm going to bring the minus sign out and make this 2x dx, and adjusting with minus a half. Now if you need to go through more work to do that, go ahead. So we have the, do it on scratch paper. The natural log of x plus 3 minus a half times the natural log, it's 1 over u du, x squared plus 9. But we still have this little pesky thing. And this we have to really fool with to solve, unless you use an integral table. We have 3 times the integral of 1 over, well, I'm going to write 9 plus x squared. It doesn't matter, but it looks a little bit like arctan, doesn't it? If only that 9 were a 1. Well, actually, that's no problem at all. We can get that 9 to be a 1. We'll just divide by 9. So I can take this one right here. We've got our first two terms. We don't want to forget about them, but I don't have to keep writing these. Right now we want to just get this integral here. Alright, now I want 1 plus x squared. This has got to be an arctan for me. So watch what I do. I've got my 3 out there, and I have 1 over. Now if I want to factor a 9 out, I want this to be 1. This. So I need to divide by 9. So I'm going to factor out 9 in that denominator, and I'm left with 1 plus x squared over 9 dx. I chose 9 because I want it to be 1 plus u squared. And you can see what u is. u will be x over 3. And then this is 9 times 1 plus u squared. If u is x over 3, du is 1/3 dx. So I do need to adjust with a 1/3 here. And another factor of 3 out here. And let's bring our 9 out. And what we have is, well, 9 over 9 is 1. So what we have is simply the integral of 1 over 1 plus x over 3 squared, u squared, times 1/3 dx, that's du, arctan u. So we can write our final answer then as follows. Whoops. Well, I've run out of room, so I'll write it right down here. Let me change colors. I'll go back to white. Here is the answer. The natural log of the absolute value of x plus 3 minus 1/2 the natural log of the quantity x squared plus 9. And that just became arctan u. So it's plus arctan of x over 3 plus a constant. So that's a complicated one, but one that I think you should be able to do. Let's do one more example. We have a proper rational function here, so I want to factor the denominator, and I can do that really fast. It's x plus 2, the quantity squared. Okay, so here we have a linear factor that is repeated. It's called a repeated linear factor. It's squared. And what happens with this is the following. 3x minus 1 over x plus 2 squared. It's going to give rise to two partial fractions. It'll give rise to a over x plus 2 and b over x plus 2, the quantity squared. So if you have one of the factors squared, it's going to give two partial fractions, one with that quantity to the first power and one with it squared. So we solve, we'll just multiply both sides by x plus 2, the quantity squared. We get 3x minus 1 is equal to a times x plus 2 plus b. I multiplied both sides by x plus 2 squared. Okay, so let's let x be minus 2. That's the obvious easy value. If x is minus 2, we know we're going to wipe out this term. And we will get 3 times minus 2 is negative 6 minus 1 is negative 7 is equal to 0 plus b. Well, 7b is negative 7. So we know that. Now to solve for a, well, you can let x be anything you want. Let's let x be 0. Now keep in mind you could let x be whatever you want. I'm just picking 0 because it's easy to plug in. If x equals 0, then 3 times 0 minus 1 would give me negative 1 is equal to, and I'm going to be solving for a. A times 0 plus 2 is 2, plus, and oh, I should have put minus, I guess, negative 7. B is negative 7. So we have minus 1 is equal to 2a minus 7. Adding 7 to both sides, we get 6 equals 2a, so a is equal to 3. Okay, so once you solve for your constants, then we rewrite our integral. So let's see, the original integral was the integral of 3x minus 1 over x plus 2, after we factored it, x plus 2 squared. We set up our partial fractions and solved for a and b, and putting them in now and splitting, I'm going to write separate integrals. I have 3 over x plus 2 dx, and then I have minus, well, I think I'll just take the 7 out, 7 1 over x plus 2, the quantity squared, dx. I probably should have taken the 3 out here. Let's move that out and just make this 1. All right, so the first one, well, if u is x plus 2, du is dx, so this is 3 times the natural log of the absolute value of x plus 2. And this integral here, if u is x plus 2, du is dx, and this is simply u to the minus 2 du. So we integrate it by using the power rule. So we have minus 7 times, okay, u is x plus 2, raise negative 2 by 1, and we get minus 1, and the reciprocal of minus 1 is minus 1, plus a constant. So let's write the answer, and that's it for this. 3 times the natural log of the absolute value of x plus 2, and then it becomes plus 7 over x plus 2 plus a constant. That is what we get after factoring the denominator, solving for the partial fractions, and integrating each partial fraction.